Okay, acid-base indicators. So if we're to get a good endpoint, an endpoint nice and close to the equivalence point, we've got to pick the appropriate indicator. The indicator that's going to change colour, give us a first permanent colour change at exactly the right time. So we can see from this visualisation that how the colour changes gradually. So if we've got bromothymol blue and we start off with an acidic solution, keep on adding base until we get to the neutralisation point, we see the colour changes gradually from, in this case it looks like around about 6.5 to somewhere around 7.5. So we're always going to get that gradual colour change, and our job of course in doing the prac is to pick the first permanent colour change. So we see that methyl orange changes colour down between 2.5 and 4-ish. So that's good where you've got an equivalence point that occurs with a pH around that. Phenolphthalein, on the other hand, doesn't begin changing colour until you've got a pH of 8 or 9. So that's only good for titrations where the equivalence point is at a significantly basic pH. Now, chemically, you don't need to know too much about this. It's just the fact that these acid-base indicators are weak acids and their conjugate base, and the two forms of it are a different colour. Due to conjugate double bonds, like many coloured compounds, and it goes from pink to yellow. Data book I think calls the pink form red for some reason, and it's going to be pure pink fall below 3.1, pure yellow fall above 4.4. In between those two pHs, both molecules are going to be present, it's an equilibrium, and the colour is going to gradually change between pink and yellow as you're moving up from 3.1 to 4.4. Or the other way, of course. So, to get the right indicator, you need to choose an indicator which gives you a clear colour change really close to that point at which the chemicals are present in equal numbers of moles. So the endpoint, which is where we end the titration, the first permanent colour change, has to be really close to the equivalence point when exactly equivalent amounts of the acid and base have been added according to their mole ratio. You have a lovely table of indicators from your data book. So I suggest you get that out now and open it up, as the work that we're doing for the next few minutes will be coming from that table of indicators. Now, what you're after is a scenario where adding 1 drop of solution from the burette causes a significant change of pH as it enters this pH range. So what you need, if you've got a solution at pH 6.3 and it's a basic solution, you're adding acid to it, so the pH is going down. You're starting off at the base end, so you've got a yellow solution. Now you want this pH range to be the one where adding 1 drop at this point is going to drop the pH significantly into that pH range. So get the pH down to 5.5 with the addition of 1 drop. Sodium hydroxide in flask with methyl red. means the pH, it must drop below 6.2 really quickly. Now, if you want to work out what colour it's going to be, what pH is going to be, think of what the main solution present in the conical flask is, because that's what the indicator is measuring the pH of, whatever solution you've got in that conical flask. Now, we're going to graph this in terms of titration curves. Now, titration curves are just measuring the pH up the y-axis and the amount of solution added out of the burette along the x-axis. Now, the graphs are in two halves. Each half has got a particular shape. Now, if it's a strong acid or a strong base that's predominating at the time, so that's in excess in the flask, then it's going to be a nice sharp log curve. Remember, pH is a log function, so graphically it's going to show that shape if it's a strong acid or a strong base. pH will change sharply near the equivalence point as the concentration of the strong acid or strong base drops exponentially or logarithmically around that equivalence point. Weak acids or bases are acids and bases that exist in an equilibrium with their conjugate, and so they're poorly ionised. Solution's effectively acting as a buffer, and so the pH just changes gradually throughout the titration. You don't get that lovely sharp log shape, you get a much more gradual increase. Organic acids and bases are universally weak. So we'll be titrating them with a strong inorganic acid or base. The thing that we're working out the concentration of is always going to be weak. So the standard solutions are going to give nice log curves. The things that we're analysing for are going to give a gradual change. So we'll start off just with the classic. This is not an organic titration at all. But what do we see? We see two lovely log curves. Now we look at that graph and straight away we can tell what's coming out of the burette, what's in the conical flask. What does the pH start off at? pH starts off at 14. That's very basic, and that means it's the base present in the conical flask, and clearly that means sodium hydroxide in this case. That means we're adding HCl to that conical flask. The pH keeps on dropping, so that means HCl is in the burette. So you'll get that just by looking at the initial pH each time. Strong acid, strong base, log curves, equivalence point at pH 7. So we can see that the sharp part of the curve goes between somewhere like pH 10 down to pH 4. So you've got a huge range. You can pick quite a wide range of indicators here. It just has to enter the base end of the pH range, somewhere between pH 10 and pH 4. So the high number of the pH range for that particular indicator has to be between pH 10 and pH 4. So you wouldn't pick the ones at either end. You would pick the ones in the middle. Phenol red begins changing at 8.4. The base end gradually turns from red to yellow. Bromothymol blue, just a bit lower, starts changing from the base end, which is where we're coming from, at pH 7.6 and goes from blue to yellow. Now we could have picked methyl red just as easily, or even the ones a little bit higher or lower, but again, ones in the middle of that range are going to be the safest choices. Now we get a situation with organic bases. they are almost always amines. So we've got to titrate it with a strong acid. So we've got a weak base and a strong acid. Now, what do we see? We see a high pH to start off with. That means the base is in the conical flask, the acid is in the burette. And with the base in the conical flask being a weak base, we see a gradual, slow decrease in pH right throughout the titration. Now, as the ethanamine reacts, it forms the ion, CH3CH2NH3+, and that's a weak acid in itself. So as it gets produced, it drops the pH of the solution down a little bit. So at the equivalence point, where neutralisation has occurred, because of the presence of that conjugate acid, the pH is a little bit below 7. So weak base, strong acid, the equivalence point is going to be below pH 7. And then when we see the acid take over, at this point the acid is in excess, we see a lovely log curve. Indicator, well, it's going to need to enter the indicator colour change range from the base end at something like pH 6 or 7 or below. So between pH 7 and pH 4 probably, yeah. And so that means in the middle of that range we've got methyl red, and we're going from the base colour, which is yellow, to the acid colour, which is red. And that is the indicator that's always used for this titration. Okay, this time we're doing organic acids, which are almost always carboxylic acids, and we need a strong base, so sodium hydroxide. So again, we're starting off with a very high pH in the conical flask. Doesn't always have to be that way. I've just happened to have chosen a few examples here in which it's always bases in the conical flask. It could easily be the acid. So we see sharp log curve again for the strong base. We see a gradual decrease at the end for the weak acid. Because the organic acid, its conjugate base is the ethanoate ion, which is going to be present at the equivalence point, which is going to end up, it's a weak base, so it's going to increase the pH at the equivalence point. So that's going to be at somewhere well above 7. And it's going to push the curve up. So we need to pick an indicator which starts changing colour at pH 10.5 and 7. Excuse me. And thymol blue. The second colour change on that, the high end colour change. So 9.6 is where it enters the thymol blue colour change range, which is a really good point in the middle, pretty close to the equivalence point. Steer clear of phenolphthalein for this titration, because phenolphtalene's colour change is colourless to pink, going from acid to base. Going from base to acid is going from pink to colourless. Now, it's really difficult to pick the point at which the phenolphthalein first begins to go a little bit more colourless. You can't really pick that point, so you can't really go from the base end with phenolphthalein. Okay, do the questions, and I'll get back to you with the link for the solutions.